Hello students, welcome back. This is going to be a very short lesson. We're going to talk about L'Hopital's rule. Here we go. Let's increase the font a little bit. Okay, that's much better. Here's L'Hopital's rule. If you have a 0 over 0 type or infinity over infinity type, and of course f and g have to be continuous and differentiable and everything, then limit of the fraction f of g is equal to limit of the fraction of the derivative f prime over g prime. Do you see those primes here? Please do not get confused with the quotient rule. This is f prime over g prime. Okay, let's do some exercises. How about this problem? This is going to be a very simple problem, and let's do it. How do you calculate this limit? Well, this is a 0 over 0 type limit. Denominator is going to 0 clearly, and numerator is going to 1 minus 1. Secant of 0 is 1, so this is also a 0 over 0 type limit. So we can apply L'Hopital's rule. The derivative of denominator is of course 1. And the derivative of numerator, this one drops out. What's the derivative of secant function? It's secant times tangent. Please remember this formula. Derivative of secant is secant times tangent. Okay, let's put in some numbers. Secant of 0 is 1 times tangent of 0 is 0 and denominator is 1. So what do you get? The answer is 0. Easy. How about the next problem here? Almost equally easy, as a matter of fact. We have this fraction of polynomial over exponential, and let's take the derivatives. Derivative of denominator, it stays as exponential. Exponential never changes. How about the numerator? We have 2x plus 1. Now, it looks as if this is inconclusive, but almost every student must have seen it okay, because x squared plus x dropped down to 2x plus 1, and it became simpler. And of course, if you take the derivative once again, it's going to go down even simpler into just 2. So what do you get? Exponential always stays downstairs the same, so we get 2 over infinity, and that's 0. Okay, we went through a couple of examples where the limit is 0. I hope we get an example that we don't have 0 anymore. Let's see if that is the case here. Okay, how about this limit here? Is it 0 over 0 limit? Yes, it is true. Please check. The numerator is going to be easy. Cosine of x is 1/2, so 2 times 1/2 minus 1. Denominator is a little bit harder to check, but that's going to be 0 over 0, believe me. Okay, alright, let's calculate. Derivative of the numerator. Well, 1 goes out, and this cosine function becomes negative sign. So there goes the derivative. How about the denominator? This minus 3 drops out, of course. And we have to calculate the derivative of this sine squared function using the chain rule. The outer function is power function, so 2 comes out, so we have 8 sine of x, and by chain rule we have to multiply the derivative of the inside. That's cosine. So in the end, what do you get? We have simplification. The sine of x cancel out, and then 2 over 8, that 2 cancels out. Okay, plug in x equals to pi over 3, what do you get? Minus 1 over 4 times 1/2, isn't it? Cosine of pi over 3 is 1/2, so you're gonna get 1 over 2. That's gotta be the solution. Let's check. Yes, it is. Oh, by the way, this is Mathematicus verification. Okay, that's good. Okay, how about some other problem here? We have some 0 times infinity type limit. Okay, alright. L'Hopital's rule always works for fraction, so you'll have to change it into a fraction. And the very first problem here is really straightforward. There's nothing even to think. This is equal to this divided by the exponential function. E to the negative x, you can always push it downstairs as e to the x. Now we have infinity over infinity type limit, and we can apply L'Hopital's rule. It's the very same limit as something we saw before, but for argument's sake, let's just complete it. 2x plus 1 over exponential, and then once more 2 over exponential. So this is 2 over infinity. That's 0. Easy computation. I cannot say the same to the second one, however. By the way, this is one of my favorite problems. I picked up this problem for the exam, or something like this problem in the exam, a number of times already. And I don't do that every semester, of course, but this has really high probability of seeing. Well, you will see some L'Hopital's rule problem here, but exactly what kind of problem will show up, it varies. This kind of thing, some log function, and then 0 times the infinity type, and this is very typical. Let's study this. Now, we have 0 times the infinity type limit. This is 0, and this is going to negative infinity. Okay, log of 0 going down to negative infinity, okay? So you have to change it into a fraction form. How do we do that? One way to change it is to keep this x upstairs and then push this log of x downstairs. Did I do this right? I just made a mistake that I saw a lot from a recent exam that I gave. This expression and that expression are not the same. You see, a times b is not equal to a over b. You see, this is not equal to a over b. But this is basically what I did. A times b is equal to a over b. If you look at this, then this is ridiculous. Nobody will make this kind of mistake. But surprisingly, a lot of people made this mistake in the exam. That's not right. How do you make it right? Denominator had better be 1 over log of x squared. So if you take the derivative like this is what you're going to get. Numerator is going to become very good because what do you have here? Oops. Derivative of x is just 1. That's very good. And the derivative of denominator, on the other hand, oh my, that's going to be a problem. At this point, I'm going to throw in the towel. You see, the purpose of this L'Hopital's rule is to make the computation simpler. And what is the derivative of this 1 over log of x squared thingy? I clearly made it worse than before. So this is not working out. Okay, pushing this log of x downstairs did not work out very well. So what do? Let's do the opposite. Keep this log of x squared upstairs and then push this x downstairs by making it as 1 over x. Or, better, x to the negative first power. You see, power form is always more useful in differential calculus. Okay, let's do the derivative. Okay, let's go over to the next step. Take the derivative of denominator. It's minus of x to the negative second power, just a power rule. And how about the numerator here? 1 over x squared. And by chain rule, you have to multiply the derivative of the inside. That's 2x. Shall I simplify this a little bit? Okay, let's do that. Denominator, okay, that's pretty much set. This one, let's see, 2x over x squared. So if I consolidate everything into a power form, I'm gonna get x to the negative first power. You see, that's gone, and then I'm gonna get just first power. So in the end, you're gonna get 2x to the negative first power. We're almost there. We get negative 2 and then x to the first power. No more denominator, so plugging x equals to 0, I get negative 1 times 0. Okay, the limit is 0. This didn't work out, but if you push x downstairs and keep log of x squared upstairs, then it'll work out. I wouldn't say this is easy, but it's still manageable. The next problem, similar. My suggestion is to keep log of x upstairs, because if you push it downstairs, you're going to fall into the same trap. You're going to get something worse than before. Tangent of x, on the other hand, if you go downstairs, it simply becomes cotangent. Not too bad at all. You have all those trig identities and everything.